completed worksheets 1 and 2. Before we get started on the new things, are there any questions about those? Okay, fair enough. Then let's just get crack-a-lack in here. All right. What was I going to say? So, in the last time we met, we had talked about compound interest, and we had established this kind of compound interest formula, right? So, one of the nice things about this compound interest formula is it's the first time that we've seen that we have the ability to dole out kind of when that exponential growth or decay would be occurring during the year. So in this compound interest situation, if we have 10% growth and we're compounded weekly, that 10% of growth is kind of incremented or divided up evenly among the 52 weeks of the year, so you don't get the exponential growth happening all at once on one day, but it's incremented out in 52 little sections of growth throughout the course of the year. Now, what we'd like to do is think about this even more and extend this idea even further. So suppose we're talking about a biological system or biological situation. And say we're talking about a population of some organism. Let's say, for example, the population of humans on the planet Earth. So how many humans are there on the planet Earth?
7 billion.
About 7 billion. Okay, great. And that population is doing what? Is it growing or shrinking? It's okay. How does the population, or what causes the population to grow?
Life expectancy growing.
I think you're thinking too hard.
Increase in children.
Babies are being born, right? Right? And specifically, more babies being born than what? People dying. Great. So, you got 7 billion people on the planet. How often do you think that something is happening to that population?
Every second.
230,000.
Well, every second.
How many people die?
So you think only on the even seconds there's something happening? People dying or babies being born?
Well, that's just like a rough estimation.
Would it be more often than a second?
Yeah, possibly. Yeah, not every.
Out of 7 billion people, yeah.
Because it's
Okay. Could it be so a half a second, a quarter of a second?
maybe a second of a second, millisecond.
So you think only on the even milliseconds?
Well, yeah, if a bullet gets shot through 2 people, the person that gets the second will be a millisecond before they die.
Right. Sure. But so only on the even milliseconds then things are changing.
Well, no, it would be I don't know. I feel like I'm in the deep end of more knowledge here.
I think more often than that.
You think so? More often than a millisecond? I can see it, but maybe not every day. You know what I mean?
I think at every instant,
Yeah.
realistically, something would be happening.
No, I can see that. Yeah.
So if we talk about an instant, how many instants are there in a year?
Instant?
Yeah.
Instant. Maybe say so.
They said 4 times a second, or 4 people are born a second.
And one person dies.
And then 2 people die. 4-2 ratio.
2 in ratio.
Okay, but when we say, so again, if we're talking about instants, how many instants are there in a year?
What's an instant?
What is an instant?
A second.
I think it's more frequently than a second. Or an instant is more frequent than a second.
Oh, like
100
More frequent. More frequent.
1 millionth of a second.
More frequent.
Infinity of a second.
There you go. Whoa. So how many instants are there in a year?
Infinity.
Infinite. Okay. So what we're going to be interested in for these biological systems, where realistically something can be happening, some growth or decay could be happening at any instant, right? It's not going to happen like all the babies are born on Monday of each week. That's not how it works. Or everybody dies on Friday of every month, the last Friday of every month. Like, that's nonsense, right? In a biological system, stuff can be happening at any time, all year long, and it won't be even or periodic or like it all happens at the top of every hour, something happens, and it just doesn't work like that. You guys all kind of agree with? So what we're curious about is then what happens when n equals infinity, right? That's what we really want to have, is where the number of compounds, the times when things are changing, when that population is growing or decaying, is any time at all, right? Everybody's okay with that idea, that notion? So let's try to figure out what that means. So we're going to say, just to make life easier, we're going to fix our values for P, R, and T to just be 1. So that leaves us with that. Everybody's okay there? And again, we're still interested in what does that equal when n goes to, or when n equals infinity. Now, can we plug infinity into this and get a number? So, we can't do that. But what we can do is we can plug in progressively larger and larger values for n and kind of see what happens. Everybody okay with that idea? So I'm going to use Excel to kind of do this. So this column, these are the 2 columns we're going to be looking at. So this is my column for n, and this is my 1 plus 1 over n to the n column. Are we okay with that idea? And since we're using like progressively bigger and bigger values of n, I'm just going to do powers of 10. So the first n I'm going to do is n to the 0, and then n to the second, and then n to the third, etc., etc., etc. So I have 1, 10, 100, 1,000, 10,000, 100,000, a million, 10 million, etc., etc., etc. Okay with that? And I think by that point we'll have a good idea of kind of what's going on. Sound good? So when I plug 1 in for n, I just get 2. When I plug 10 in for n, I get this 2.59 and change. Everybody's okay with what I'm doing? So that wasn't a lot of increase going from 1 to 10. We only went from 2 to 2.59, right? Let's see what happens when you go from 10 to 100. Even less of an increase, right? So I can tell right now, like this number, whatever this 1 plus 1 over n to the n, is slowing down as n's getting bigger and bigger, right? That's indicating to me that this is going to actually settle down on some specific number. Everybody's okay with that notion? Reasonable conclusion to reach. So if I go from 100 to 1,000, even less change, right? The only place that changed was the 100 spot. Going from 1,000 to 10,000, the only thing that changed was the thousandths place. Going from 1,000 to 10,000, the only thing that changed was the 10,000 place, the fourth decimal place. Everybody kind of see what's going on? So each time we increment up, basically, like, the only change, we're seeing the first few decimal places are all the same, and then like this later decimal place, each time it's getting a little later, changes, right? When comparing the previous number to the new number. Everybody agree with that? So how many decimal places do you think this number 1 plus 1 over n to the n is when n is an infinity? How many decimal places long do you think this number is going to be? A lot. How many? A lot. More than 8. No. Infinity is the correct answer there. It's going to be infinitely long decimal. Okay, let's keep going. So we can kind of keep doing this kind of as long as we'd like, right? And if we look at the numbers in our decimal, does anybody see a like a repeating pattern in the numbers in this decimal? If I'm looking at just this 2.718282053, does anybody see a pattern? The whole thing. What do you mean the whole thing?
Like the 71828.
No. We're not comparing successive values in this column. I'm just looking at this value, singular value, and looking for a pattern in its decimal. For example, like if you look at 1/3, that's 0.3 repeating, right? Where it's 0.3333333. Or if you looked at, like 1/6, that's 0.166666666. Or if you looked at 11 or 1/11, that's like 0.0909090909. Do you guys see a pattern like that going on in the decimal, where like you have a sequence of numbers repeating over and over and over again? No. Good. So, what do we call one of these numbers that has infinitely many decimal places, and there's no pattern in the decimal? There's no repeating pattern in the decimal. We have a special name for this kind of a number. It's called an irrational number, right? That should ring a bell. So, other examples of irrational numbers, yes? Sure. Other examples of irrational numbers that we're familiar with, one of them might be pi, right? Another might be like the square root of 2, or the square root of 3, or the square root of 5. These are all examples of irrational numbers. Notice what's in common with all of these irrational numbers. I'm not listing the decimal, right? I have some kind of shorthand name that I'm giving that number because the decimal is infinite and it doesn't repeat. So we're going to do the same thing here. We're going to call this number E. So I'm going to use the lowercase letter e to represent that number. Oftentimes we'll call this number the natural base, or the natural base. Or sometimes we'll call it Euler's number, named after Leonhard Euler, who is the mathematician that kind of did the foundational work for this. He's on my Math Hall of Fame back there on the far right, second from the, or the third from the bottom. So on the far right, third from the bottom. Leonard Euler.
Oh, so from the bottom. Oh, okay. I was looking at.
So 5 over, 3 up.
I was looking at here.
If we're talking about graph, his location would be 5, 3. Everybody so far so good with what this number E is kind of representing and why we were interested in kind of developing this. Hopefully that's some good context. So what we have now is a new, or the foundation to a new model. So P is again like our initial amount. E is this number 2.718 yada yada yada. R is our rate of change as a decimal. And T is our time interval. So this is like a new model that we can use. Okay, so under ideal conditions, a certain bacteria population increases by 94% every hour. If you place 100 bacteria cells in ideal conditions, how many bacteria will you have at 6.5 hours? Well, since this is a biological situation, we're going to use our new model. So we have the initial is 100 bacteria, and then our rate of change is 94%, but I have to write that as a decimal, so 0.94. And then the time is 6.5 hours. Again, this is per hour and this is hours, so I don't have to do any unit conversion to make everything match. So I just go ahead and type this into my calculator. And just like the number pi, the number E is built into our calculator, which is lovely. So I'm going to do 100 times, and then if you look on the left-hand side, you'll see the button with the letters LN on it. Above that button in blue is the letter, you'll see e to the x. So if I press second and that ln button, I get the e and an exponent already put in there for me. So I can do that. So what do I got? 45,034 bacteria. Yuck. We've got an epidemic going on. Everybody okay with that idea? So again, just like the stuff we've been doing before, we just have a new model, right? Want to hear something gross?
Yeah.
So you know how many cells you have, like human cells you have on your body? You have, I think it's more or at least equal to number of bacteria cells growing in and on your body. How's that? Does that give you the willies a little bit?
Yeah, not really. I feel like I already knew
You might have already known that. Anyways, I think that's a willy stat right there.
Right now.
Anyways, obviously they're not all bad bacteria. There's lots of harmless or even helpful bacteria. But a biologic situation isn't the only time we might use something like this. There's lots of things that we might describe using like this kind of continuous change. So how many of us have had like a chemistry or earth science class where you've talked about radioactive decay? So radioactive decay, you have an element or an isotope that's unstable, and slowly it emits some radiation either in the form of mass or energy, and decays, turns into either some lighter isotope of the same element or potentially a different element, depending on the type of radioactive decay. But this is something that happens kind of continuously, because if you think about even a very small sample of an element, like 1 gram, which is a tiny amount, how many atoms are in that 1 gram? Like orders of magnitude, right? Like 10 to the 23rd is a mole. So like, all maybe like, 1 gram is like 1/200th of a mole, but 1/200th of 6 times 10 to the 23rd is still a stupid number of atoms, right? So, again, so many of them. They're all kind of decaying at, the same rate, but like they started at different times, and like there's just constant decay happening. Another common example might be you don't even need to necessarily talk about like these biological or even like natural science related situations. There's still, you could talk about banking still. Suppose that you have like So let's say, suppose you invest $5,000 in an account that pays 5.5% interest, compounded continuously, how much is the account worth in 15 years? So the place that you want to pick up that's different in this problem than the previous ones that we saw in the previous homework is this phrase of compounded continuously. Specifically, if something is compounded continuously, how many compounds are there per year? Infinitely many. So we should be using this new model as opposed to our old compound interest model. Everybody okay with that idea? That's my little keyword for knowing that I need to use this one instead of the old one. So I plug things in, 5,000 for the initial amount. R is 0.055, and then T is 15. Oops, my goodness gracious. That's not right. Forgot to do times e to the 0.055 times 15. Jeepers are creepers. So 11,409.40. Everybody okay there? So again, the trick is just making sure you're reading the question, keeping in mind which of our models do you need to use. Is it the general growth or decay? Is it this compound interest formula or this new continuous change model? It should be relatively easy to tell which one to use based on the context of the story problem. Again, the continuous change is for biological or natural life or natural sciences kind of situation, or unless you hear the word like continuous somewhere in there, like continuous compounding or something. Graphing. So we can use E to do graphing. So our general form for exponential growth or decay looks like this, where the B now is going to control our growth or decay. What happened here? Sorry guys, OneNote froze on me. I've caught this new computer doing that on a too frequent basis. Then decay, B less than 0, A greater than 0, or B greater than 0, A less than 0. So it turns out that actually it's possible to take any exponential growth or decay problem that we had written before and turn it into this form. Now that's beyond the scope of what I'm going to ask you to do in this class. But I just wanted to point out to you that, like, that anything that we were doing before, you could do this way now. Which is fine, whatever. So let's look at a graphing example. So we can do the graphing where I have E here. Almost everything is going to be the exact same. So here my A is 2, my B is 0.5, and my K is -3. Since my A is positive and my B is positive, this is growth. And my horizontal asymptote, I know, is always y equals k. Now I'll make my table. Now, when we made our table before, I did like h minus 2, h minus 1, h plus 1, and h plus 2. Here I have no h, right? So I'm just going to take the h's out of that plan. And I'm just going to have minus 2, minus 1, 0, 1, and 2. So minor modification, but like no big deal. It's still basically the same pattern. And then I'm just going to go ahead and take these values and plug them into my function and write down the y to get the y values. So you notice that when we're doing this, we're largely getting like some big kooky numbers. That's fine. I would just round these to like 1 decimal place is good enough for our purposes. Everybody's okay with that notion? The fact that E is a irrational number is what makes the makes these numbers get so kind of hairy here. So you'll almost always get a bunch of kooky looking numbers when you're doing this, and that's okay. We're just going to round it to like 1 decimal place and go on about our business. Unless it's clear that like I should be rounding it somewhere else. You know what I mean? Like one of them's 0.12 and the other is like 0.17. It's like, well, maybe I need to do 2 decimal places here and have like some really small scale or something. But and we'll put in our asymptote at -3. So -2, -2.3. -1 and -1.8, 0 and -1, 1 and 0.3, and then here's my curve. Everybody's okay with that? Basically the same as what we did before, right? No major modifications. The domain, since it's exponential, is always going to be all real numbers. And the range, just like before, just depends on A and K. So since the A is positive, I know this is going from K to positive infinity. So all the graphing stuff is still basically the same. No big deal there, right? The model stuff, still basically the same idea, right? We just have a new model. And this is where we're going to end today. I think this is probably enough of an idea.